Hello and welcome to episode number 19 of CS350 Online. I'm your host, as always, Leslie Eisted, and on today's episode, I've decided we're going to talk about assignment 3. But before we get into assignment 3, let's look at our OS of the day. So we finally reached a point where we can actually talk about operating systems that you probably have used before, like macOS. And I am going to assume that probably over 50% of you out there have actually used macOS at some point in your life if you are not currently using it right now. Now, as you know, macOS is a product of Apple, and it was released in 1984. And I mentioned before that the desktop environment that you see in Apple was actually inspired by the Xerox Alto, which we talked about a few weeks back. Now, it's very interesting because if you look at the Apple operating systems, they can be subdivided into two distinct eras. There's the classic era, and then there's the current era, which is known as the Mac OS X era. Now, the classic era, which is probably predates many of your computing experiences, this is actually where originally they started storing the operating system on a ROM chip. A ROM chip, by the way, is a read-only memory chip, and it's what that let them do is, because the operating system was either in whole or in part stored on a chip in hardware, that gave them a huge performance advantage, as you can well imagine. Now, another interesting thing is that even though it was released in 84, they didn't actually support multiprocessing until 1987. And even then, they didn't support multi-threading until 91, and even at that point it was cooperative concurrency. And if you remember, cooperative concurrency is when you have you actually have the user programs actually have to voluntarily yield. So there's not going to be any preemption here. This is going to be you yield, you block, or you exit, and those are the ways that it actually happens. Where you get the sharing. Now, they didn't also have virtual memory either until 1991, so they made some pretty big updates in 91. So pre-91, they weren't using virtual memory, and that seems like it makes a lot of sense because the majority of the OS would have been stored on the ROM chip, so it would have been part of hardware. People weren't concerned about security and so on. So that era of the classic version with cooperative concurrency and a really flat file system and all of those things, that kind of ended right at the end of 2001, and Apple decided they wanted to create a Unix-based operating system. So they actually acquired Next Step, which is a BSD-based operating system. And that the first Unix BSD version was released in 2001 as the first Mac OS X. And because it was built on top of BSD, it got all of the lovely features that BSD already had. So you got preemption, you got protected memory, you got security and networking and all of those things. And Apple, of course, went in and they made their own changes to that. But yeah, it's still BSD underneath. And that's why things like having a bash terminal is so easy to do, is because underneath it's just BSD with some changes. Now, they did keep the file system between Classic and Mac OS X, which is this HFS, but in the last few years, Apple has actually released a new file system called APFS. And the reason why they released a new file system was because their original file system wasn't optimal for solid-state drives. And so APFS is a solid-state drive file system, so it shouldn't be run on non-solid-state drives, or at least that's what I've read. This, by the way, is the first version of macOS, and if you're looking at this here, this actually looks really familiar, because one of the things I think Apple's done really well with their operating system is they've created a really successful branding. And what I mean by that is the look and feel of their OS is the same, and it's consistent no matter which version you're using. So this is Mac OS 1, But at the same time, while I'm looking at this, there's the Apple menu in the upper corner. And while there's some color and some other obvious features missing, for the most part, you look at this and you know how to use this if you've ever used an Apple product before. And then this is kind of the end of the classic ones. And yeah, you've got Explorer here because Windows decided that they wanted to make sure that their products were available for Apple as well. And now we start to see things like the dock at the bottom. But other than that, I mean, these two look a lot alike. All that look and feel is still there. And if you were to switch out to your regular desktop, you'd see that exact same look and feel. So that's kind of fun. All right. So we're going to dive then right into talking about assignment 3 here. So assignment 3, by the way, that is the last assignment in the course. And a lot of people actually argue that assignment 3 is easier than the previous one. I have mixed opinions on that. But let's talk about it. So let's go single page, full screen. Okay. So first off, a couple things I do want to mention about assignment 3. So as you know, all of our assignments build off of each other. And the same is true for assignment 3. So assignment 3 is building on the back of A2B, which builds on the back of A2B, A2A, which builds on the back of A1. So if you don't have any of those working, then you wouldn't be able to get full marks for assignment 3. However, what I want to tell you is that if you didn't get argument passing working from assignment A2B, don't worry because there's no argument passing in assignment 3. So we only run Hog Party. We're not going to run arg tests or arg test. So don't worry about argument passing from exec v if you didn't get that working. And we are also going to be running wide fork. So wide fork and Hog Party are actually the only two tests that we are going to run that use any of the process management calls that you implemented on A2A and A2B. And if you actually look at the mark breakdown, and we will look at it in a little bit, you'll see that that doesn't actually make up a lot of marks. So if you didn't get A2A and A2B working, I want to say relax. And if you really are stuck with that code, I almost want to encourage you to revert to assignment 1's code and then build A3 on assignment 1. And then if you have time, try to build A2A and A2B features back in. But I'm going to leave that decision up to you entirely. So with that little disclaimer out there, a couple things to talk about. What is assignment 3? So all of our assignments, unfortunately, in this course right now, cover the first half of the course. We don't actually have any assignments from the second half of the course, although we are hoping to change that in the future. The assignment that you have to do now is to fix the virtual memory implementation for OS 161. In particular, as I have mentioned a number of times, OS 161 does not actually free memory. And it doesn't free memory because it doesn't actually keep track of the memory that's available and the memory that's not. Which means that once you free it, you actually have no mechanism to go back and use it. So you're going to obviously need to fix that because we would like to be able to actually free memory. But there's a number of other quirks with the virtual memory implementation. I mean, it's called dumb VM for a reason. It's dumb. So first off, you might recall that our MMU uses paging even though our operating system is using segmentation. And we talked a little bit about how you shove segmentation down the throat of a paged MMU. It's not too difficult. But the TLB on our MMU, which has 64 entries, once it's full, the operating system panics. So if it's trying to insert something into the TLB and there's no space for it, there will be a panic and the operating system will die. And we both know that that does not make any sense at all. So what we actually want to happen, of course, is we evict somebody. But right now we just panic. In addition to that, here's a very interesting quirk. The text or code segment of the user address space is not read-only. So that means that if the user program accidentally tries to overwrite part of their program code, it is actually permitted, and it will cause the program to run incorrectly, which is why it's so important right now for you to get those addresses in the user space correct. But obviously this is a problem because we know that the code segment of an address space should be read-only. So we don't want the user to be able to do that. So we're going to need to fix that. And then of course, the big problem, as I've already mentioned, is not being able to reuse memory. And then one final issue. I see these slides need to be updated. So I'm going to update these slides. It says no need to fix this in W20. This is not W20, this is S20. So please ignore this statement here. The final part of this is actually using, right now we're using segmentation, and we want you to switch this to paging. Actually, you know what? The best thing that I could do here is, instead of using last term's version of these slides, I'm just going to bring up an older version. It'll just take me but a moment to grab them. Of course, assuming I can remember where I put them. There we go. All right, that's a little better. I'll post these ones up as well, so that way there's no confusion. All right, so let's start at the beginning. Now, one of the things, and I reiterate this for each time we actually run these assignments, it's very tempting to sit there and just write all the code for the assignments all at once. Please don't do that, because you're going to run up against bugs, and you're not going to be sure where those bugs are coming from. So implement this as the slides are showing you, and because we want to make sure that you implement one slide, make sure it works before you move on to the next one, because otherwise you'll never find the bug. So step number one, and you can do this literally right now, it's a very quick fix, is we want to fix the TLB problem. So we are going to handle our TLB exceptions in VM fault. That's going to be in the dumbvm.c file. And inside of VM fault, you'll see close to the bottom of the function, there is actually a for loop. You could just open it, right? So let's open it. I'll show you it. So let's go into Arch, MIPS, VM. So that's where we are. We're in kern Arch MIPS VM. And we're going to open dumbvm.c. And let's go down to VM fault. Helps if I can spell. There we go. There's VM fault. So this is where we're actually going to figure out which segment the address space is a part of, and then we're actually going to do the translation and then update the TLB. Well, near the very bottom of this function, what you're going to see is, and this might already be edited here, this is edited, doesn't work though. You'll see this for loop, and that for loop is actually going to be responsible for searching the TLB and finding an empty entry. And if it doesn't find an empty entry, then what it's going to do is cause a panic and die. And if it does find an empty entry, then it's going to insert itself in there. I apologize, that was actually some old code. I was tinkering around helping a student debug, so that there actually doesn't work. It's been edited for a bit. But I just wanted to show you where in VM fault you could find that for loop. It's right at the bottom. So what you need to do to change this is, if while you're searching the for loop to try to find an empty TLB entry, what you're going to want to do is, when there are no TLB entries, instead of panicking, you need to select one of the TLB entries and evict it. You do not have to implement a cache eviction strategy. What we want you to do is call this function here TLB random, and TLB random is going to randomly select an entry and evict it and insert yours. And that's it. So that's it. That's how you fix the TLB replacement problem. All you're going to do is call TLB random. Do not panic this time. So you want to make sure you're getting rid of the panic and call TLB random instead. And there you go. Part 1 done. Should take you 5 minutes, right? Okay, so now that you've got TLB replacement done, what's the next part that you have to do? The next part that you should have to address is the read-only text segment. This is the second easiest part of the assignment. So right now, if you remember, we have a TLB entry, and the format of the TLB entries is specified in the virtual memory module. There's this TLBLO dirty bit. That is actually used to indicate whether the pages are read or read only, like read write or writable. So by default, we have this bit on, and that means that the pages can be read and written. And the problem is we want those pages that belong to the code segment to be loaded read only. So we need to turn the dirty bit off for read only pages. And look at this, there's a nice little bit of code here that you can add that actually does the job. You should note that if we're giving you code in the slides, you should probably follow it. But here's the trick. You don't want to flip that bit for every TLB entry. You only want to flip this bit if the TLB entry is for something in the code segment. So my recommendation to you is to add a flag to VM fault at the beginning of the function, and that flag just is a flag to indicate, is this the code segment? And then if you have a code segment address, set that flag to true, and then inside of that loop where you're trying to insert your new TLB entry, if the entry corresponds to a code segment page, then simply flip the BIP, and otherwise don't. It's really easy, right? That's like 1, maybe 2, 3, 4 lines of code, depending on how you do it. So, real simple. But it's not that simple. So here's the problem. Let's suppose that you are loading the address space. That is, you are loading things into the address space for the first time. And the problem is, if you so I'm trying to write the first byte of my program code to the code segment of the address space. And that's going to cause a TLB miss because we've never written to this address before, so we get a TLB miss. And on the TLB miss, I'm like, oh, this is the code segment. So you set the TLBLO dirty bit to being off so that you get a read-only page. And then, of course, you return from the exception because now that entry is in the TLB, and then the CPU is going to retry that translation. And when it retries the translation, it's going to throw an exception again because now you are trying to write to a read-only segment, and that's a problem. Because we're trying to load the code segment, and except by setting the TLBLO dirty bit to off, initially, we're preventing ourselves from loading the code segment. So you're going to need to do something else. You want the code segment to be writable until it is loaded. And at the point where the load is finished, then you want to flip it to being read-only. So how we've suggested that you do this is to add a flag to the address space structure. And that flag is going to indicate whether or not the address space has actually been loaded. That is, has load elf completed or not. If load elf has not completed, that segment should remain as read write. And the second load elf is done, you can switch those to read only. Now, this is the tricky part. So after load elf, you'll be flipping a flag in your address space to indicate load elf is read only. But here's the problem. Your TLB is going to be full of entries that correspond to when the code segment was read write. So we want to make sure that going forward after loading the code segment, that the code segment is considered read only. Now we could go through the TLB and modify all those TLB entries, but it's much easier to just clear the TLB so that the next time we try to load the code segment, it will fire an exception and the new TLB entry will be loaded as read only. So after load alf, set a flag to indicate load alf is done, and then clear the TLB. And you clear the TLB, of course, by calling asActivate, horribly named function. And then inside of dum VM and VM fault, you're going to set that dirty bit, not just when it's a code segment, but you're going to set it when it is in the code segment and load alf has completed. So it's going to be a pair. Right? That's still not hard. It's just some flags. So there's one final piece. What happens on your computer? Let's suppose that you managed to compile some code, and in your user program, you tried to write to read-only memory. So you tried to overwrite the code segment accidentally. What happens when you run that program? Does the program crash? Or does your operating system panic and die? Do you get a blue screen of death? Because you and I both know the answer. You don't get a blue screen of death, usually. Your program dies. But right now, OS 161 is actually set up such that if a user program tries to do something bad with their memory, like write to read-only memory, the OS crashes. That's dumb. That's really dumb. So what we need to do is we need to modify it a little bit more to make sure that when the user process tries to write to read-only memory, it's not the OS that crashes, the program gets killed, and the OS keeps running happily. So right now you'll actually see inside of VM fault that when you get that VM fault read-only exception, it causes a kernel panic. Now the panic doesn't actually happen right here. Normally what happens is an error code gets returned from VM fault, and then that gets picked up by mipstrap, which passes it forward to kill cur thread. So what we want you to do is we want you to remove the panic from dum VM, and we want to have you add an appropriate error case to VM fault such that it returns an error to mipstrap, and mipstrap will forward that error to kill cur thread. And then inside of kill cur thread, we want you to actually kill the current process. Now how that's going to work is going to look a lot like sysexit. And I actually see a lot of people calling sysexit inside of kill cur thread to actually solve this problem. However, that would actually be wrong to do, because if you are killing a process because it's done something bad from memory, you're not calling exit. So calling sysexit doesn't make sense. However, you could modify sysexit to parameterize the exit status code. So you could have sysexit take either W exited or W signaled, or however you want to kill your processes. And then inside of sysexit, just make a teeny change so that instead of always using mkwait exit, you can use like mkwait signal or mkwait exit, depending on which kind of exit status was passed in. That's up to you. But one thing I will say is don't call exit without modifying it. You could copy and paste it and make a new version for being signaled or killed. It's up to you. I'm just giving you some general recommendations, which I've seen work out pretty well. At the end of the day, this is actually fairly straightforward because you've implemented 99% of the code for this already. All right. Now, at this point in time, you should have written very few lines of code. Very, very few. Like 50, maybe. You should have the TLB not causing a panic when it's full, and the operating system should be able to handle processes now that try to write to read-only memory. Okay, so we've solved two major problems. Now we need to attack the biggest problem, and that is the fact that OS 161 doesn't actually manage the memory. So these slides have some pictures on them, and I'm going to show you the pictures, and then I'm going to go over to OneNote, and we're going to talk about strategies for how to manage memory. So if we look at how much physical memory we actually have available to us, it's this big chunk. While the kernel is booting, we call it the bootstrap process, the kernel is going to allocate a bunch of memory. It calls this function getPages, which you really, really need to work with. You're going to want to make some big modifications to that for this assignment. And getPages to allocate memory calls this thing called RAM steal mem. RAM steal mem literally just grabs some memory. So there's kind of a pointer that says where is the next free address. And RAM steal mem, if you call it and say give me 2 megabytes, it simply returns its current address and then advances that pointer by 2 megabytes. And that pointer never moves backwards. So when they call it steal mem, they mean it's permanently stolen. Even if you call free on it and it gets marked as dead beef, you can never go back and reuse it. So RAM steal mem is taking memory away forever. But that's the problem is, so after bootstrap, each call to kmalloc ends up calling getPages, which ends up calling RAM steal mem, which means that pointer keeps getting advanced, and we never actually go back and free our memory. And we want to be able to free memory so that we can reuse it, so that we don't have like a cap of 32 threads. We want to be able to run lots and lots of processes. We want to be able to run processes back to back. And right now, as you know, in OS 161, you can't run tests back to back. It runs out of memory. This is why there's no memory management at all. So we want you to implement the memory management. And on assignment 3, we are going to be running your tests back to back because we're expecting that you fix this. So how do we actually do this? So we know that the system actually keeps track of things in terms of pages and frames, even though we technically use segmentation in OS 161. So you can imagine that all the remaining memory that's left, you could subdivide it into a bunch of pages. Now, to figure out how much memory you have left after the original bootstrap steal mem, you can call this lovely function called RAM getSize, and it'll give you the low address and the high address. And that will tell you how much of memory you actually have available to dish out to all the people who call kmalloc. Doesn't seem too bad, right? But now we need some mechanism to actually keep track of that. And that is going to be what we call a core map. Now, a core map is a data structure, and you have total freedom over how this is implemented. But what you're going to do is the core map is going to keep track of which frames are in use and which frames are not. And then the idea is we store the core map right after the bootstrap memory. And then anytime when we do a request for memory or a free, we are going to go through the core map to manage that request. So I'd like to break out now to OneNote to actually show you some different things with that. So let me grab my pen. Hopefully this program isn't going to crash on me today. Loves to crash. A grid is a good idea. There we go. So let's look at some memory. So let's say we want our core map to store we want to keep track of all of the pages of physical memory, and we want to know which ones are actively in use right now and which ones are free. So core map, we'll call this version 1. So let's suppose our core map contains a mapping from the frame number, and it simply indicates in use or not. So let's do frame number, and then we'll keep track of in use. So we've got frame 0, 1, 2, 3, and so on. And then we can have this be a Boolean. So 0 is not in use. These are in use. These are not in use. Okay. This is a nice idea, but it doesn't actually convey all of the information that we want. And the reason why it doesn't convey all the information that we want is when you call malloc, and let's say it goes over here and you say, give me 4 pages. We can say, okay, find 4 pages that are contiguous in nature, and we'll return the address. But when you call free, we don't tell free how many pages to free. Somehow, magically, free just knows how many things it needs to free. How does it know that? Well, it knows that because the core map keeps track of contiguous allocations. So this here does not track contiguous allocations. So it's not going to work. So let's do core map version 2. All right, so now let's keep track. We'll still have our frame. We'll still have in use. But now I'm going to keep track of, is this allocation part of a contiguous allocation? And if so, what number is it? So we're going to say it is page X of. Now what this is going to do, so let's draw our frame numbers again. So what we're going to do is we see that we have this in use. And so let's do 0, 1, 1, 1, 0, 1, 1. So let's say that these 3 are part of a contiguous allocation, and these 2 are part of a contiguous allocation. Well, let's say this one is not. So what we're going to do is the page X of, this is going to be page 1 of 3. This is page 2 of 3, and this is page 3 of 3. And this is 1 of 2, this is 2 of 2, and this is 1 of 1. And the idea is, so when we're allocating these contiguous blocks, we have to look for a contiguous block of pages that matches that size. And then we'll update this in the core map to say these are now in use and they're part of a contiguous allocation. And then when we free, the free is always assumed to be given this address here. And the free can then look at the core map and say, oh, this is 1 of 3. And then it will free this. And then this is 2 of 3. And it will free that one, and so on and so forth. So free needs to be able to look at the core map and figure out exactly what needs to be freed. Okay. So that's version 2 of the core map. And this can work, but don't do this. Why have I drawn a great big X through this one? Because it seems like it does everything we're going to want. It keeps track of which frames are in use and which ones aren't. It lets us keep track of contiguous allocations for free. But why doesn't it work? Well, this doesn't work. I mean, it technically works, but the problem is it uses a lot of memory. So you're storing a frame number. You're storing a Boolean here for that, and then you're storing 2 integers. So most people are going to be using 3 plus ints per entry. Three plus ints per entry. That doesn't make sense because if you're using 3 plus ints per entry, you're using a lot of space. So let's look, one note crashed, by the way. Let's actually look now at another version of the core map. Now, I'm not going to tell you how to implement this. I'm simply going to show you an example of using it. And this version of the core map is going to use the minimum, almost minimum amount of space per entry. So, and that's important because we're going to squeeze how much physical memory you get for this assignment. And so if your core map is really big, you may end up using the majority of your memory just to store your core map. So you really want to make sure your core map is as teeny tiny as possible. So let's do core map version 3. I'm not going to store the frame number anymore. The frame number is simply the index. So what my core map is going to look like, so this is simply the index into my core map. is not stored. We will keep an address to the start of the core map. That's all we need. And then we can calculate the index based on that. So we are not storing the index, but just for the sake of comparing this to the previous model, I'm going to write the indexes down. Go. All right. Now, this here is what we are actually storing in the core map. Let's use black again. 0, 1, 2, 3, 0, 1, 2, 1. That's it. Now, what's interesting is if you are a free block, we mark you as 0. There's no point in having a separate in-use flag. We can simply use 0. Then for a contiguous allocation, you'll notice I didn't do block 1 of 3, block 2 of 3, block 3 of 3. Look at this. Starting at the start address, which you can always assume you get, the entries values increase. That means that these, since they are increasing, we know these are part of the contiguous allocation. The second you go from 3 to 0, or 3 to 1, or 3 to something else that is not 3 plus 1, that is not 4, we know that the next frame is not a part of this contiguous allocation, and so we would stop. So in this example here, 1, 2, and then when we look at index 7, we see it's a 1, which means it is not a part of that allocation, and so we stop. And so for this core map, per entry, I only have 1 integer stored. Pretty simple. There's some additional details to this. I will let you figure those out. Once you have your core map, though, that's not enough. You're going to have to store it. Where do we store it? So right after the kernel steals its memory for the bootstrap process, that is the position where you're going to want to store your core map. Your core map is going to take up a certain amount of space. You're going to need to estimate how much space it's going to take. And then you're only going to want to manage the space that follows the core map in the core map. And it's entirely possible that in between where the core map ends and the actual managed memory begins, there is some empty space, and that's totally fine. One of the things I want to remind you of is that all pages and frames must have page-aligned addresses. That is, the addresses must be divisible by the page size. Otherwise, it won't work. So you may have some blank space between there. Now, how and where do you create this core map? So you want to create the core map in some time inside of VM Bootstrap, probably after the kernel does its steal mem. So there's going to be a point in time in which you don't have a core map, and if the core map is not created, you want to make sure you're using steal mem. But once that core map is created, you want to make sure that every future memory allocation goes through the core map. So I recommend having a flag to indicate whether you've created your core map or not. Now, a lot of people like to modify kmallocs meat and potatoes and kfreeze meat and potatoes to do the next bit of work. But my recommendation is for doing allocations or requests from the core map, actually modify getPpages, because some of the address space functions call getPages directly instead of calling alloc kpages. And so it's just easier to modify getPpages. All right, so you've created your core map. Now, if you're sitting there, how do I actually allocate the memory for the core map itself? Well, you don't need to. Because at the point where you are loading the core map, all memory in the system is yours. All of it's yours. So when you're loading the core map, when you're creating it, you don't need to call malloc because the memory is already yours. All you need to do is compute the addresses and write to them. So keep that in mind. Now, actually modifying alloc and free to make use of the core map. Now, alloc k pages, I wouldn't, as I said, a lot of people like to put the code required to search the core map and actually allocate those entries from the core map. I would recommend against doing searches and allocations for frames in alloc k pages. I would instead modify get p pages and just have alloc k pages call get p pages, which I think it does already. So, and the reason for that is, again, because something else in the address space just calls get p pages directly. And if you only modify alloc k pages, then your address space won't actually work properly. So pay attention there, make some clever decisions. When you're allocating, remember that alloc k pages is asking you for a block of contiguous pages. So if you call alloc k pages with 5, that means I want 5 contiguous frames of physical memory. So make sure you're giving contiguous memory for this. Then we have free k pages. Now free k pages, you're going to have to find that contiguous block in the core map and you're going to have to mark it as free, whether that's changing all of the values to 0 or what have you. Again, this is why, because we don't specify how many pages you need to free, that's why your core map needs to keep track of contiguous allocations. And that's it. That's actually it. At this point, after you've implemented your core map and you've modified get p pages, alloc k pages, and free k pages, you should have a memory management. And that's pretty good, right? Okay. There's one final part of the assignment, and we are expecting that you do this final part. I'll make sure to clarify that on Piazza shortly. The final part is page tables. So one of our big problems is that we're using segmentation. Now, ironically, we actually have no tests for this. But segmentation, as you know, it does introduce fragmentation. How we implement segmentation inside of OS 161 is instead of we're just allocating, a start and a limit for each of the segments, we are allocating segments as contiguous blocks of pages. And what we want you to do is add proper paging to this system. We don't want you to get rid of segmentation. We want you to merge segmentation with paging, which is actually a decent implementation of virtual memory. There are some really interesting side effects of doing this. For one, you're going to have not one page table, but you're going to have a page table for each segment. And since you have a page table for each segment, and each segment only keeps track of the memory that's in use, each page table only needs to keep track of the valid pages. So your page tables are going to be very meaningful because the page tables will only contain valid mappings. So they're going to be small and meaningful. That's an advantage, right? So you're going to have a page table for each segment, and you're going to know exactly how big each of those page tables need to be. And then what we're simply going to do is when you allocate the segment now, you're going to, instead of just writing to contiguous memory, you're going to be writing to contiguous virtual addresses, but those virtual addresses are going to map to various pages. And this is going to require you to make a fair number of changes to the system. For one, you're actually going to need to modify the address space. So right now, these are all of the segment fields. You're going to need to modify this. We don't really need a physical base address anymore, and that's because the physical base address doesn't have a meaning, because each page now is going to map to a different physical frame. So now we're going to want to get rid of this and replace it essentially with a page table. So make sure you replace each of those with page table pointers. You're going to, during your AS create, you're going to want to initialize, is responsible for initializing the address space data structures. But it's very difficult to actually allocate the space for the individual page tables if you don't actually know how big those segments are going to be. So you can't really allocate the page tables in AS create. But in AS define region, you can, where it actually says how big the region should be, you can actually allocate the space for the page table. And if you want to set up individual read-write permissions on a page level, you could do that. Please don't. There is absolutely no reason for you to have per page read-write permissions. Keep the segment read-write permission that you already have. There's no reason to do this. Our system isn't that sophisticated. So once you've actually allocated the space for the page table, then in AS prepare load, where we are actually doing the loading of the segment of the address space, that's where you can actually allocate the physical frames of memory for that particular segment and fill in the page table entries. Now, something to note. So we'll go over to OneNote, which is, of course, crashed again. It's starting to get really irritating, to be honest. So what you're going to do then is inside of AS prepare load, when you are allocating the physical memory, right now you'll see that it does something like alloc K pages 7, or it might say that's what it does. This gives you a contiguous block. That's a segment. We don't want a contiguous block. We want each page to map to a separate frame. So what you need to switch it to now is something like this. You're going to allocate each page individually because you want each page of the virtual address space to map to a random frame to remove the problem of fragmentation. Which means that after each of these things here, you might imagine that you need to, per page, update the page table entry, and so on and so forth. So that all needs to happen on a per page basis, which means that, you know, for AS prepare load, we are individually allocating the pages. And so in AS copy, we would normally just do one big mem copy from one contiguous block of memory to another, but we can't necessarily do that anymore because in physical memory, we don't have a contiguous allocation anymore. Now it's scattered to the wind, so you need to make sure in your implementation that if you need to make changes to AS copy, you do so. And remember that our frames are now scattered to the wind. And that means that when you are destroying the address space, you must not just call AS just like destroy K-free on the whole thing or free K pages and then free the page tables, because that won't actually free anything. You'll only free the first page. What you actually need to do is call free K pages on each and every individual page. So you'll have to iterate through your page table and you'll have to actually call free on each entry. And then you can free the page table as a whole. So there's a little bit more work here. Now, kind of the last thing that we like to talk about is make sure that you are always using the correct kind of address. You should never, never read or write a physical address. The MMU assumes that every address you give it is a virtual address, which means that the MMU is going to try to translate every address you give it. If you give it an address that has already been translated, it's not aware, and so it's going to try to retranslate it. So while you are going to need to compute some physical addresses, never read or write to a physical address. You'll have a very bad time. So what you would do is something like convert using some handy macros that exist in the operating system already. You're going to be able to convert physical and virtual addresses. You will convert the virtual addresses to a physical address. You can perform your calculation there and then convert back before you do the read or write. So please do make sure that you are never actually reading or writing a physical address. You are only going to be reading or writing user or kernel virtual addresses, but never a physical one. Now, let's talk about the grading on this assignment. That's actually really important to talk about. So if you look at the marking report, which I have it open here, there are 50 marks assigned for this assignment, and you will see that the only tests from previous assignments that exist are wide fork and hog party, and those are the only ones that use exit, fork, wait, PID, and execv. So only 5 out of 50 marks, so it's 10% of the assignment, actually correspond to things from previous assignments. So if you don't have these features working, I wouldn't panic too much. Get A3 working and then revisit the other things. Now, we have no argument passing, so if you don't have argument passing working for A to B, don't fix it because there's no gain for you. Now, the remaining marks are divided between these tests for basic memory tests. We have a read-only memory write test, a couple of those. And then we have physical memory management tests. And those are going to be run not just once, but we're actually going to run these multiple times without shutting the OS down. So we're going to squeeze how much RAM you get, and please do look in the hints page because we tell you how much RAM you'll get. So we're going to squeeze it down, and then we're going to run these tests back to back to back to back to make sure that your memory management actually works properly. And the idea is that if your memory management doesn't work and you're not actively freeing everything and having the ability to reuse it, then we won't be able to run these tests back to back to back. For this assignment, we are only using one CPU. So there's no reason for you to test on 2, 3, 4, or more CPUs. You only need to test on one CPU because that is all we are using. Now, the last little bit. You can actually get 100% of this assignment working without implementing the page tables. And the page tables are probably the most code you have to write. It's actually pretty easy code. However, because there are no tests that we can run to test whether your page tables work or not, we are actually going to be inspecting your code. So that means a TA is going to open up a certain select group of files. VM fault needs some changes for one. The address space is going to need some changes. So we're going to open those up and we're going to take a quick peek to see, number one, did you implement it? And number two, are you using the implementation? If you decide not to do page tables, whatever score you get, we take 5 marks off. So it's a 5-mark penalty for not doing page tables. So if you get 50 and you didn't do page tables, now you get 45. If you got 40 marks on the test and you didn't do page tables, now you have 35. So it's a 5-mark penalty for not doing page tables. That's assignment 3. Some notes about assignment 3. You are going to need to make a number of changes for page tables to VM fault, because right now VM fault uses segmentation to translate addresses, and if you're going to use paging, then once you identify which segment the addresses is in, you're going to need to do a page table lookup. So there's lots of little things like that, lots of little details. Probably the hardest part of this whole assignment is getting the core map correct. So that is computing how big the core map should be, figuring out how to search the core map, how to free things in the core map, and so on and so forth. Now, some common errors that I see come out in assignment 3 switch out here. So common errors that come out in assignment 3. If there's any point in your code where you created something but you neglected to initialize it, you're going to find out about that on assignment 3. Because now that we have the ability to reuse free memory, you can't make any assumptions about what the initial value of that memory held. So if you had a Boolean and it worked for A1 and it worked for A2A and it worked for A2B, but you forgot to initialize it to false, you're going to find out it doesn't work on assignment 3. If throughout A1, A2A, and A2B you never called K-free because you knew it didn't matter, that's going to give you a hard time as well, because we're squishing the memory and you're not actually going to be freeing anything. So it's really important that you come back and you actually properly free memory everywhere where you were supposed to. If you did something like a process table to do process reusability, or just to keep track of all the processes in your system, make sure that your table is 64 entries or smaller, because number 1, you're going to run out of entries, and number 2, you don't want the table to be you want it to be 64 or less, not more, because you don't want the table to be too big because we're squashing how much memory you have. And at the same time, we are going to be running processes back to back, so you don't want it to crash. I can safely tell you that 64 entries is more than sufficient. Some other errors I see common in this assignment are people are calculating addresses and then trying to write to a physical address. It's a really common mistake when you're actually building the core map. Make sure that you never read or write a physical address. It doesn't work. Another common mistake is I've seen a lot of students actually keep track of the frames that are used for the core map in the core map. So you actually have the ability to, the core map itself might take 1 or 2 frames. And let's say the core map takes 2 frames. Well, what I've seen happen is students actually have entries in the core map that correspond to the 2 frames that the core map is using. But they've forgotten the fact that the core map is using those frames, and so those 2 frames are marked as free. And what ends up happening is that when you call allocate pages, one of the core map frames gets repurposed and then the core map gets corrupted. So that's actually a pretty common thing. You should never manage the core map's memory in the core map. The core map memory doesn't need to be managed, because the core map is going to exist from the point of time that the OS boots to the point of time where the OS dies. So there's no point in actually managing the memory for the core map itself. And then another really common mistake is that I see a lot of people not doing their page and frame addresses as multiples of the page size. And that's going to cause a lot of kernel panics. So do make sure that you use things like rounding to make sure you have addresses divisible by the page size. All right. So question on Twitter or Twitch here is, so it's possible to get a total mark of -5 in A3. Yes, I suppose it is. I don't think that's ever happened. No, that's only for testing. So obvious, I've never seen it happen. Honestly, I've never seen anybody get -5. It's capped to 0. I will personally cap it to 0 because negative marks, that's just cruel and unusual punishment. And I've had that happen before. I have had an exam, it was 251, where if you didn't do it, you got 0. If you did it and you got it correct, you got positive marks. And if you did it and you got it wrong, you got negative marks. And that sucks. So I will cap this to 0. You're not going to get negative marks on this assignment. That's cruel. That will just, typically speaking, this if you fall into this boat here, you usually have passed half of these. And if you're getting the code inspections marks, it means that you majorly failed a lot of things. So obviously you probably didn't get the page table part. So the maximum test there is usually 24. So don't worry, there will be no negative marks. All right. So with that, I don't want to start anything else new because I don't want to start anything else new. So that is the end of talking about assignment 3. If you found that you want to hear this again, so obviously this episode gets, like all episode, gets uploaded to YouTube, but we also have the fall of 2019. There's an A3 guide there as well, and you can go through that. There are probably student questions in that one because it was done in front of a live studio audience, but then it was done in front of class during those days where we were allowed to be in person. So you've got a couple guides now. And again, we are expecting that you do the page table part. So this -5 marks for not doing it is fair game. That being said, if you don't do it, I'm not going to be judgy. I mean, if I had done this assignment when I took this course, I would have seen this and I would have been like, I'm not doing that. But that's up to you. That's really up to you. And just so you know, questions about assignments are fair game for your final assessment, which is an auto-graded learn quiz, which I should probably do. So just keep that in the back of your mind, that even if you don't do the page table part, it's still fair game to ask you questions about how you might do it. But it's going to be like multiple choice questions or true-false questions, so yeah. All right, so I'm going to end things there then. On our next episode, we're actually going to start a new topic. We're going to start the topic of file systems, which is how do we actually store the data on the disk? How do we implement things like permissions and so on and so forth? So with that, we will see you on Thursday.
Today we celebrate the first glorious anniversary of the information purification directives. We have created, for the first time in all history, a garden of pure ideology, where each worker may bloom, secure from the pests, obeying contradictory thoughts. Our unification of thoughts is more powerful a weapon than any fleet or army on earth. We are one people. One will, one resolve, one cause. Our enemies shall talk themselves to death, and we will bury them with their own confusion. We shall prevail.
On January 24th, Apple Computer will introduce Macintosh. And you'll see why 1984 won't be like 1984.